So this is about joint work with two analysts, Genaro Lopez Acedo from Sevilla and Adriana Nicolae from Cluj in Romania. Some of you might have heard me talking about this, but I think very few. Some more heard Adriana talking about this topic in Oberwolfach, but I just saw the audience is quite different from the one, so the overlap is not too big to the ones who attended earlier this month a meeting in Oberwolfach. And anyhow, Adriana focused more on the geometric aspects and the history and so on of the problem, and I might focus a bit more on the logical aspects. So anyhow, this is about the so-called lion-man game. So what does a lion-man game consist of? It goes back classically to Radu, and it has been discussed in Littlewood's book, Littlewood's Miscellany, and he describes it as follows: a lion and a man in a closed circular arena have equal maximum speeds. Which tactics should the lion employ to be sure of his meal? So here the question was whether the lion actually can capture the man, so at some stage the distance between the lion and the man is 0. We will actually later consider a variant of that problem. For a long time, it was believed that the answer is obviously yes, the lion can, but there was a mistake in the proof, which was uncovered by Bisikovic in the 50s, and then it actually turned out that the lion cannot eat the man, although he can get arbitrarily close. So I will not really talk about this historic problem and why is one interested nowadays still in these kind of problems, because this is actually a prime example of a general class of problems, so-called pursuit-evasion games, and they play a certain role in robotics, for example, where you can have also several lines and several men, so to speak. And basically in robotics, to avoid an obstacle is some sense similar, it's some sense dual to actually getting to a point like a line. And so there is research in this connection, but also it revealed some interesting geometric features. And so the starting point of our collaboration was a paper, which I was not an author of, other people involving Adriana and Genaro, where they focused on characterizing certain geometric conditions in terms of the lion-man game. Okay, so that's this point here. So I'm here particularly interested in the connection between the geometric structure, which will be very general, so not like a circle on the plane, and the lion-man game. Good. Yeah, as I mentioned, there are various ways, there are continuous, discrete things. We will use a discrete lion-man game. There are, variants to the effect that there could be several evaders, more pursuers, and there can be physical capture, like in the original Radu game, or in our case, it will be epsilon capture. So the point is whether the lion can get arbitrarily close to the man, and the question then will be how long this takes for a given epsilon. And also there are different degrees of freedom in the movement of the lion. So we focus on a discrete time, equal speed game, and epsilon capture. And so the setting is that of a geodesic space. Actually, it is just that of a metric space, but it helps to think first in terms of geodesic spaces. And if the space is not geodesic, the result still applies, but there might actually be no lion-man game. But we come to this later. But the formulation as such can be given just in the language of metric spaces, and that is very useful for the actual logical treatment of that whole situation. So our domain is now, for the time being, a geodesic space, and the lion has an initial position L0, and the man has an initial position M0, and we fix a bound on the distance the lion and the man may jump. And then we request that, in the after n steps in the move, the lion is now approaching the man. along the geodesic from the current position of the line and the current position of the main. And of course, the line cannot move further than d. So d is the upper speed he can have. But if that's possible, so if the distance is still further than this d, the line will actually go by d. And if the distance is just smaller than d, it will just hit the main and go directly to the main. And from that moment on, the distance is always 0. So to be on a geodesic means to satisfy this condition here, so that L1 plus 1 is a kind of in-between point between Ln and Mn. This means that, you know, this right-hand side distance, which in general will be strictly greater than the left-hand side by triangle inequality, is actually an equality. So if this is on a geodesic, then this is satisfied. And in general, one could say, if whenever you have in a metric space the situation that whenever there are 2 points, x and y, there are such midpoints, then one can actually, by iterated use of this, show that there must be a geodesic, at least under some completeness assumptions. But the situation as such can be formulated also completely without referring to geodesics, just as a metric condition. If the space is not geodesic, then this might never be satisfied. So in that case, there might be no line-main game. But we can just abstractly say, a game is just any pair of sequences of line moves and main moves which satisfies these metric conditions. And if the space is, for example, uniquely geodesic, like in the Euclidean plane or many other cases, then the line is actually completely determined what it's doing, because the line goes with the optimal speed and has then to follow the unique geodesic. So the only freedom in the game is by the man, because the man can jump at any place he likes as long as is within distance d. And so what we consider is under which conditions this distance here tends to 0. So whether the line can get arbitrarily close, and therefore epsilon capture, as the official terminology is, the man. Okay, so that's the situation. So once again, if one is in uniquely geodesic space, the Ln is uniquely fixed. If one is in a geodesic space, there are many choices the line can do. If one is in a space where there is no geodesic, then there might be no line-main game, but the formulation still works in this generality. And that really helps to think not about in terms geodesics, because it's quite complicated to calculate with them, rather than just these very simple metric conditions. And by the way, of course, please interrupt me whenever you have any questions. So this is what I just said, is uniquely determined. Okay, now the starting point of our collaboration was this paper by Renaro, Adriana, and Bucena Piatek from Poland. And they proved that if X is a compact, uniquely geodesic space, satisfying a slightly obscure but actually important property of betweenness, we will see in a minute what that is, then actually the line wins. And this betweenness is actually critically needed. If you drop this, then there are counterexamples. And so they asked me, I mean, they gave talks about this in Darmstadt, and asked me whether proof mining could be helpful here to get a speed of a rate of convergence. In fact, it turns out that this sequence decreases to 0. So convergence is actually for all exist statement. One can drop the innermost quantifier, so proof mining should apply to give a rate of convergence. However, I first expected this to be, very messy, because the proof uses an iterated application of Bolzano-Weierstrass argument to format limit points and then to set up a new sequence and to subsequence, and that is again a limit point. You have a new subsequence, and then you have this sequence of all these limit points, and you apply monotone convergence to that sequence. So it's a nested use of arithmetic comprehension, which of course can be done. So it's clear that there should be a rate of convergence definable, let's say, in Gül's T plus bar recursion. So because bar recursion, though only of lowest type, is required to give a functional interpretation of arithmetic comprehension. So I said, yeah, of course we can do this, but it might be very messy. Fortunately, I looked then a bit more into this, and it turned out that things are not messy at all. And this is actually now for me one of the prime examples of what I called before Corona strike. This was in last year in the ASL Logic Colloquium in Prague. I gave a talk on what I call proof-theoretic tameness, namely that in many situations where in principle it could have happened that one gets a weight function extracted which has some huge complexity. In practice, this very rarely happens, and almost all bounds are actually where you get actually a rate of convergence, some kind of polynomials in the data. And we will also see this feature here. So first of all, one can certainly extract things, but in order to extract, so the first insight here is that one should actually, one should upgrade the notions of being uniquely geodesic and having the betweenness property to uniformized versions of those, which if one has a compactness assumed, as one has here, would be equivalent to the original notions. But that's automatically what these proof interpretations we are using in proof mining, like monotone or bounded functional interpretations, do. And often it turns out that the use of compactness is sort of self-inflicted because one uses properties which are not uniformly stated, so they depend on an actual point. And then one has to actually construct points which kind of encapsulate some infinitary information, which then would be limit points and so on. As soon as the notions are properly uniformized, that might disappear. And this is what happens here. It turns out that the compactness can be removed altogether. So the use of compactness was self-inflicted, and it can be just replaced by the much, much weaker assumption that the notions of being uniquely geodesic and the betweenness are upgraded to uniform, uniquely geodesic and uniform betweenness, as we see is in all practical cases automatically given, despite of the fact that in almost all cases you never have compactness. So that is the thing. This doesn't always happen, but it happens here. I mean, there are cases where the result actually is false. The convergence itself is just false if one doesn't have compactness. A prime example is in fixed point theory, the so-called Kasper-Zelsky-Mann algorithm, which features in optimization under the name of, in a generalized form, under the name of proximal point algorithm. There one can do proof mining. One can also avoid sequential compactness arguments and give reasonable quantitative results. But the results depend on still the assumption of the space being compact, which is reflected by the fact that the extracted rate will depend on the constructive quantitative version of being compact, being a modulus of total boundedness. But here, the compactness disappears altogether. So one has a qualitative improvement of the statement. So the statement has nothing to do with compactness. It works in much more general situations. Also, the uniqueness of the geodesics can actually be dropped. And since you don't have uniqueness, you don't need uniform uniqueness. We nevertheless see that the uniqueness is a particularly important source for getting the betweenness property, but there are situations of non-uniquely geodesic spaces which are also covered. And then one can actually give a modulus of a rate of convergence, which basically only depends on some quantitative version of this uniformized betweenness property, which we call a modulus of uniform betweenness. So everything, this is the only thing which really matters, on which the situation depends, in addition to the obvious things. I should also say, of course, instead of compactness of A, we at least have to assume the boundedness. So that's what is said here. So we need a bound on the diameter. Actually, you only need, you know, some 4 points or something to bound. I mean, it's a very local boundedness, but let's, for simplicity, assume the whole set is bounded. Of course, it also depends on the speed and it depends on the epsilon, but the only data from the geometry of the situation which enter is this modulus of uniform betweenness. Yeah, and I mentioned already that this is pi 2, and therefore we can apply proof mining. So proof mining guarantees that we can extract such a thing. And now the question is, of course, under which circumstances can we actually get such a theta? And on proof mining, it is also important not just to say, if I would have this nice input data, then I could produce my bound for the goal, but also whether that input data can actually be achieved can be extracted itself by proof mining in the usual situations where one applies these type of things. And in fact, it can. And one big class of spaces which satisfy the betweenness property are strictly normed spaces. So whenever you have a strictly normed space, so a strictly normed space is basically a space where if you take 2 points on the unit ball and then take a midpoint, then this has norm less than 1. And so that's strict convexity. And this generalizes also to geodesic spaces. For geodesic spaces, strict convexity is not enough to ensure the betweenness, but some notion of convexity of the metric is needed. However, this can be written as a purely universal condition. And so now you have strict convexity, which is for all exist, and universal implies betweenness, which we haven't seen yet, but we'll see in a minute, which is also for all exist. And now by functional interpretation, based on measurizability, like in monotone or bounded functional interpretation, what this translates into is, if you have uniform strict convexity, which is called uniform convexity with a modulus, then you actually get uniform betweenness. And the strict convexity is only the truth of it is only used because it's purely universal. So in that situation, extracting from a proof of Adriana, who had shown in a previous paper that if you have a strictly convex geodesic space with a convex metric, then that has a betweenness property. It immediately follows by proof mining that it will have the uniform betweenness property, and to actually get a modulus if you upgrade a strict convexity into uniform convexity, and you have a modulus for that given. So that is another class of actually highly non-uniquely geodesic spaces, which have the betweenness property, are so-called Ptolemy spaces, which we'll see later what they are. They satisfy an axiom, which is a theorem of Ptolemy in the usual space. And when I saw this result, I immediately said, well, then we have uniform betweenness. Why? Because being a Ptolemy space is a universal axiom, and one can apply proof mining to this type of space as a kind of abstract class of spaces, and to conclude that one has a uniform betweenness with a modulus. And there's a very complicated example, which I was interesting on R3. One can define a slightly strange norm, which shows that strict convexity is actually strictly stronger than the betweenness property, because one might think the usual spaces which don't have the usual spaces which are not strictly normed also don't have the betweenness property. But one can actually come up with a space which has a betweenness property despite of being not strictly normed. And again, here one can use proof mining to extract. And in all these cases, the thetas will be very simple. It will be quadratic of order p, something of that sort. Good. So now, since not everybody might have heard me talking about proof mining, I am inserting here a couple of slides on proof mining. So this is concerned with the idea, going back to Kreisel's program of unwinding proofs to extract new information from prima facie non-constructive proofs. And so this new information might be effective bounds on a for all exist statement or algorithms, or also qualitative improvements on the data and so on. And in our case, being a bound and an algorithm is the same, because being a rate of convergence is a monotone statement, and because of the decreasingness, it has this for all exist form. And in order to deal with the situation, like a statement, whenever you have a geodesic space X or a Ptolemy space X, one has to deal with abstract types. So abstract spaces which are hardwired into the formal system by an extra type. So, some years ago, we showed how to do this for metric and normed and so on structures. And because these structures are not assumed to be separable, which is actually critically here used for the uniformity of the bounds, they cannot be, represented in the usual style bare space representation. So they have to be hardwired. So one sets up a typed extension of Peano arithmetic, but not just over the old types like in Gödel's T, over the natural numbers, but also over such a base type. And if one is prepared to use bar recursion, then by Spector one can even add the axiom of dependent choice and hence countable choice. And hence, since we are classical logic, all comprehension about numbers, so full impredicative comprehension about numbers is here. So we have full classical analysis. And then one adds on top, axiom stating X is geodesic or Ptolemy or whatever. And then one can design a notion of keeping track of hereditarily bounding information. So what does it mean to be bigger than an element, or to be a bound on a point in a metric space, when in a norm space it's clear the number should be an upper bound on its norm, but in a metric space no point plays any special role. So one has to define this as a ternary relation relative to some reference point. So one takes some point in the space as a reference and then measures distances relative to that. And then, like in Howard's measurizability, this is then upgraded to, extended to all finite types. And I just write here down what this means for the type X goes to X. So a measurand F star will be a number theoretic function, because the measurands are always things which operate on numbers or functions on numbers and so on. So whereas the object measurized is an arbitrary finite type object over N and X, the measurand is only a finite typed object over N, and therefore normal computability and so on applies to that. So one doesn't have to require the space to come with any notion of effective presentation or something of that sort. What one computes is on the X, not on the Y. So in the case of a self-mapping from X to X, a measurand is just a number theoretic function having this property here. And not all functions are measurizable, but many classes of functions, like uniformly continuous functions, for example, are. And let's just take a particular simple case, which however matters here in this connection already, of non-expansive mappings, so of Lipschitz 1 mappings. Then this very simple function n goes to n plus b, where b is just an upper bound for the displacement the function produces on this reference point. This simple function will be a measurand. And then logical meter theorems tell us everything we need to know about f is such a measurand. So in this case, everything we need to know about f is actually such a b. So it's very local information. And in the linear case, the reference point will be 0, because we have a norm, and the norm obviously measures distance from 0 and not just distance from any reference point. And then the goal is to extract effective bounds for all exist theorems where you have you know, some Polish space P, like the real numbers or other continuous functions on the unit interval. You have a compact Polish space K, like the unit interval. So these are things which I usually explicitly represent, and so they are done in the usual style. And then we have this abstract space. We have self-mappings, sequences, and so on. I mean, you can have also simultaneously different spaces, has been also treated, but we don't need this here. And because we use classical logic in general, this A has to be existential. So if you have a universal quantifier there, then there are needed counterexamples. If you're in a semi-constructive regime, then you can allow arbitrary things. And so the logical meter theorems, which I refer to now, establish that you get bounds on N, which only depend on X, not on the data from the compact space. So that's a kind of Fenn rule type phenomenon. And as far as the abstract space is concerned, only on this very weak here majorizing data, which we have seen here. Okay, and so that's what is written here. And what type of spaces can be treated? Well, general metric spaces, geodesic metric spaces, normed spaces, Hilbert spaces, uniformly convex and uniformly smooth spaces, and hyperbolic spaces, cut zero spaces, Ptolemy, abstract LP and C, and so on and so forth. All these spaces enjoy the right uniformity so that the monotone functional interpretation of their axioms translates the axioms into themselves, so that you don't upgrade the structure. This is in contrast to these classes of spaces. If you have a strictly normed space and you do a proof mining, then the machinery will tell you, okay, suppose the space is not just strictly normed, but let's assume it's actually uniformly convex, then I can give you a uniform bound. Yeah? So uniform convexity is kind of the fixed point for under the interpretation for this thing here. And likewise, smoothness gets upgraded to uniform smoothness. Separability actually gets upgraded to total boundedness, basically unbounded compactness. And that's why this should be avoided, because we want to avoid compactness. Good. Yeah, and then, you know, this has been treated. I had an earlier paper for mainly bounded structures in 2005, and then with Philip Gerardi, we generalized this to unbounded structures. And I just give here, this is the last logical meter theorem, and then we go to normal mathematics back. So here we have now our formal system. We prove a statement of that aforementioned form. So for every X, let's say in the reals, for every Y in the unit interval, and for every line-man game situation, there is a number such that an existential statement holds. Then we can extract a uniform bound on V, which is computable and which only depends on the majorizing data for the line-man situation, in addition to stuff from the Polish space, a name for the element, and which is uniform, again, independent from the elements in the compact space. Now, this term is actually not just computable, but it's given by a bar recursive term. And if we don't need comprehension, higher comprehension, then it will be actually primitive recursive in the sense of Gödel. And if we don't use higher induction, then it will be primitive recursive in the ordinary sense, and so on and so forth. And in practice, it will be very nice and beautiful. Good. Yeah, so maybe maybe the chairman can tell me, is this is about 50 minutes to talk or something?
Yeah, that's right.
Okay, so then maybe I skip here a little bit on uniform boundedness. We can maybe come to this later, but I now want to finally reveal what this betweenness property is. This is a slightly obscure paper. It's not very well known by these two people, in which this notion is introduced, and it plays a key role. And there were actually earlier papers on the line-man game where this was overlooked, and they didn't use this notion, and actually then they were informed that one needs this notion, because otherwise the results are actually false. So what is the betweenness property saying? So here again, we say, if think first in terms of geodesic spaces, but we don't need this. Suppose Y is on a geodesic between X and Z. This is expressed in this form here. Yeah, I mean, this is actually an equality because the other inequality, of course, holds by triangle inequality. So suppose y is in between x and z lying on a geodesic, and suppose z is in between y and w, then z is in between x and w. And the same applies for y, but this is by symmetry. We only have to write this down. So, I mean, you might wonder, how can this possibly fail to be the case? But it can actually, in non-strictly convex cases, it usually fails. So take R2 with the maximum norm. So that would be, I just write here now x instead of maximum. This would be the maximum of so if x is, okay, x is x1, x2, so that's a maximum of x1, absolute value, and of x2. Then the unit ball in this looks like this. So that is the unit ball. And now we take as our point x, we take this point as our point y, we take this point, and as our point z, we take this point, and as our point w, we take this point. Now, in this space, this is a geodesic. So y is on a geodesic between x and z. Y is in a geodesic between x and z. And likewise, this is a geodesic here. And so z is on a geodesic between y and w. But x is not on a geodesic, let's see, or what was it? Z is not on a geodesic between x and w. Z is not on a geodesic because this whole thing here is not a geodesic. Yeah, so this can happen in a non-strictly normed space. And if you just turn around the picture by 90 degrees, you get a similar example. You get the same example can be used to show that with the one norm, this is also not the case. So where this norm then would be this one. For strictly normed space, this cannot happen, as I just mentioned, and it might not happen in certain non-strictly normed space, but in general, it fails. So this betweenness fails. Okay, so now let's go to the concept here again. So being in this inequality here is a universal statement, because you can say for all k, this is smaller or equal than plus 2 to the minus k. And you can say the same here, and you can say the same here. So you have universal, and universal implies universal. So let's make this precise. And by the way, I forgot to mention, these points here should be distinct. Otherwise, this cannot hold. Actually, the only distinct which one needs is between y and z. If other things collapse into the same point, the situation becomes actually simpler or even trivial. But x and z need to be distinct. And so what we have here is, if you prenex this, it means if for all quadruple of points, for all k and for all m, there is an n, such that if the points are separated by 2 to the minus k, and if they satisfy an approximate betweenness property by 2 to the minus n, then the conclusion betweenness holds approximately with 2 to the minus n. This is just prenexing the original statement. I just wrote them with this error for all errors, the actual inequality as equivalently by saying it holds all the approximate versions happen for arbitrarily small errors, and then I just prenexed. And I wrote this here in a slightly strange way with greater or equal here and strictly less here, because there's still a universal quantifiers left here and there's existential quantifier only left here. So the thing here inside the parenthesis prenexes just as an existential formula. And so we are in the context of proof mining. We have, and for all exist, and there are further exists here hidden in these quantifiers, in these relations, which we don't care about. And so now what the proof mining would do, and that's what we therefore take as our point of departure here, is, is to extract actually a measurement on n, so a bound on n, depending just on k and m, and measurements for this. Now this statement is obviously monotone in n, so any upper bound is actually a kind of witness. And so what we actually get is the following, and that's our notion of uniform betweenness with the modulus theta. So modulus theta produces, and then now I'll go back to epsilon delta language, produces a delta, so that if we have points satisfying the delta approximate betweenness condition, then the points in the conclusion satisfy the epsilon betweenness condition. And all what we need as data is a lower bound on the separation and an upper bound on the diameter. This comes from the need of majorization. So we can choose one of these points as our reference point, but then we have to measure the distance of the other 3 points from that reference point, which means we need a bound on the diameter of the set. Once we have that, we can majorize all of them. Good. And now here's again our line-men game, now repeated. So whenever we have 2 pairs of sequence satisfying these metric conditions, we call this a line-men game. We now assume that our space is bounded by B and that we have a modulus theta. The modulus theta, just to say it again, has 3 arguments: the epsilon, the separation A, and the bound B. And now we go into this diagonal here. So we place a separation, also the epsilon, and we call this theta epsilon. And just for convenience, let n be so big that n times d is bigger than b plus 1. I mean, d is positive, and so this can be easily achieved. Okay. And then we have our main result already, namely, as promised, one only needs this modulus of uniform betweenness. One needs the speed, the allowed speed d. One needs the bound on the diameter, and one needs the error epsilon. And one has a very simple low complexity rate of convergence. So that's not a rate of meter stability. This is a rate of convergence, saying if after that many steps, for sure, the line is epsilon close to the name. So there's no compactness, no total boundedness, no bar recursion, no uniquely geodesicness. All this has disappeared. So even from a qualitative point of view, this is a far-reaching generalization of the original result. Now, uniform betweenness, to say a bit more about that. So, I mean, this is already the main quantitative result. So now I want to say more about uniform betweenness and, you know, how these thetas look like in particular cases. In a normed space, uniform betweenness can be written also equivalently in this nice formulation. And so you can also give a modulus interpretation to that. So you can make that just as you make strict convexity into uniform convexity with modulus, you can upgrade this condition to a uniform version together with modulus. And then one can actually has nice formulas translating. I mean, Diminis-White's proof that these two notions, the two non-uniform notions, are equivalent, translates under the proof interpretation into explicit transformation formulas, how moduli for the uniform versions translate into each other. So if you start with a uniform modulus delta for this 3-point condition and you do this, then you get the original notion of modulus. If you start with an original modulus, then that delta will be a modulus of satisfying the betweenness property in this setting here. You know, this thing only depends on one argument, only on epsilon. The other thing depends on the separation and on the diameter. And you see here how they enter. Yeah. Whereas here they go away because this is actually instantiated what these A's and B's are in this case. So this is in itself a proof mining of this proof of this proposition. It is guaranteed that such a thing has to happen. Now let's first discuss uniquely geodesic spaces. As I had said before, strict convexity implies betweenness in normed spaces, and if you have convex metric, also in geodesic spaces. Now, in normed spaces, strict convexity is equivalent to being uniquely geodesic. So therefore, uniquely geodesicness implies betweenness. And so this should again translate into, suppose you have a uniform version of you being uniquely geodesic, which means if you have two approximate midpoints, then they have to be close to each other. And then one should be able to construct a modulus of uniform betweenness. And in fact, this can be done. So if you have a uniformly unique geodesic space with modulus phi, then by this very simple, and you have this convexity condition, which is anyhow true in normed spaces, but in geodesic space, it's a proper condition. So if you have this very tame, again, formula here, you get actually the modulus of betweenness. So that's the quantitative rendering of the original proposition, which in the geodesic case is due to Adriana Nicolai, that if you have a uniquely geodesic space which satisfies this convexity condition, then it satisfies betweenness. So this translates into, if you have the uniform unique geodesicness with together the modulus, then you get the uniform betweenness together with the modulus. Now, uniform uniqueness, as I said, uniqueness is closely tied to strict normedness and uniform uniqueness to uniform convexity. And therefore, one can use non-uniform convexity moduli to actually calculate in many cases now these things. So this phi, so once you have the phi, this modulus of unique geodesic, you have also the theta, right? Once you have the phi, you have the theta, right? This very simple translation. And such a phi can be computed in many cases in every LP space. You have this, it's of order p. If p is larger than 2, it's of order square. Actually, if it is between 1 strictly greater than 1, because the case p being 1 is ruled out, even in R2, as we saw in the beginning. The case p infinity is also ruled out, as we also saw in the beginning, but in all other cases. And of course, these spaces do not have the property that their bounded closed subsets are compact. They are far from being compact. So only in Rn this would be the case. But we have the models of betweenness, and one can also use geodesic settings, so-called Riemannian. This is a metric generalization of Riemannian manifolds, the so-called kappa spaces. The prime example being the unit sphere. So the unit sphere is the prime example of a cut1 space. And here we have the quadratic phi. And since the phi is very low complexity, so is by the aforementioned transformation formula, so is, I mean, this theta is basically phi of something. And so if phi is quadratic, then so is psi. So it's okay. So this is, you know, all tame because there are geometric things here, not inductions, not comprehensions, which play a role here. And so finally, because we were very proud, actually this was an insight of Adriana and Renato, that they realized one could actually drop the uniqueness. Then they proved again the result without the uniqueness, but using compactness. And then I applied again the proof mining idea to eradicate the compactness. And so in total, we were able to treat these just using uniform betweenness without any unique geodesicness. Now the question is, are there nice examples? And as I said, there is this class of Ptolemy spaces, metric spaces satisfying this 4-point condition are called Ptolemy spaces. And this is related to a theorem in geometry called Ptolemy's theorem, and that's why this is called like this. These spaces are in general not uniquely geodesic. There is this paper in which they show this, they give a counterexample to this. But Adriana had proven they satisfy the betweenness property. Now, if you look from this through the eyes of proof mining, this is a purely universal condition. So you just add this X type to the system, you add this universal axiom, you express the betweenness property. The betweenness isn't for all exist property, suitably prenexed as we saw. Then the proof mining applies, and it gives you a bound which is highly uniform because it does only depend on the separation and betweenness, and that's a uniform betweenness. So I immediately could say, if that's the case, then you have actually proven uniform betweenness. And this, in fact, turned out to be true, and one can actually extract from that proof. So it cannot be that you have a uniform class of structures like Ptolemy spaces, and you prove that in all of these structures, a non-uniform property holds. This cannot be unless you actually have proven that the uniform property holds. And so this is now, again, an extremely tame modulus of betweenness. And now we see here why it's really a meaningful generalization to have dropped the uniqueness, because otherwise we could not have dealt with general Ptolemy spaces. And then finally, there is this strange example again in this paper by Dimini and White. So they ask themselves whether actually in norm space, strict convexity and betweenness are the same notions. Because if you are strictly normed, then the betweenness follows. And in the usual non-strictly normed cases, the usual suspects like L1 and L infinity, the betweenness also fails. However, in R3, one can come up with a new norm where this is different. Of course, in R3, all norms are equivalent, but this doesn't matter here because being strictly normed is not a property of the topology, but it's a property of the metric conditions of the norm. And so with one norm, you can be strictly normed, and with another, you are not, and although the norms are equivalent, of course. And so this norm, which is equivalent to the Euclidean norm, the space is not strictly normed, and hence not uniquely geodesic, because in norm spaces they're equivalent, these notions, but it satisfies the betweenness property for strange reasons. Now the proof is very complicated, and it uses many non-effective steps, case distinctions, lobbies through the middle, all over the place. But it's clear that from proof mining, it must be possible. Again, one can already say now, because this is a compact space. I mean, once you're restricted to a bounded subset, if you have a bounded closed subset, because it's finite dimensional, and because after all the norms equivalent to the Euclidean norm, you can use the usual estimates and to get a modulus of total boundedness. So this is a compact space, and therefore by the logical meter theorems without the abstract space, just keeping for the compact K, it is clear that the proof of Dimini and White must actually contain hidden a modulus of uniform betweenness. And I mean, this is very complicated. I wrote down all the details. This was 12 pages. We cut it down in our publication, which, by the way, I should have mentioned, is to appear in the Pacific Journal of Mathematics. And there's also a version on the archive. So we cut it down to 3.5 pages, leaving some exercises for the reader to do. So by logical meter theorems, it's clear that it must be possible to extract a modulus of total boundedness from this. And in fact, it was possible, and it has this form. So again, it's a very tame, despite the proof being 12 pages. In the end of the day, you know, everything is polynomial. In this one uses actually the equivalence between this norm and the Euclidean norm. For the Euclidean norm, one has a modulus of convexity, namely epsilon squared divided by 8, and that's where the quadratic feature comes from. And you know, there cannot be all of a sudden in this tame context, you know, the Ackermann function or something of that show up. So even in this case, we now have a beautiful theta. And so that's it. So here is this paper. I think this investigation into the Lion-Man game, and there are now several papers also by these co-authors and other people, and they highlighted this before, slightly obscure notion of betweenness. But it actually turns out that uniform betweenness, which was introduced in our paper by applying proof mining to betweenness, Actually, if you use this, that's what I skipped. If you use these uniform boundedness principles, which I introduced, or bounded collection, which Fernando Ferreira has been using, and which is supported by the bounded functional interpretation, then you can actually show that two notions are equivalent. Yeah? So in this non-standard or setting of uniform boundedness, which is not a classically correct principle in the absence of compactness, but which is supported by the proof mining, the two notions actually equivalent. So we believe that uniform betweenness will play an important role in the future, and it has been, you know, put into focus by proof mining. Here are some surveys, and this is our paper to come up. This was the original paper where you can look up how it was proven, the result using nested sequential compactness in this paper, and then you compare with what has been done in this paper. So we have qualitative improvements, no compactness, no uniqueness of the geodesic, just uniform betweenness, and everything is effective. Okay, and I guess that's it. Thanks.